So we want to understand trigonometry. That means we're going to understand circles and triangles. Awesome. The first thing we need to understand is what is an angle. Okay. So say we have these two rays right here. Okay. They're joined at a vertex. Vertex is just a fancy word for spot where two lines cross. I'm calling these rays. But a line just extends infinitely in both directions, whereas a ray begins at this vertex, and it's the line segment that extends infinitely from here. Between these two, we have an angle that's usually defined by a rotation. So if you were to take this right here, ray A, and rotate it with respect to this vertex, you would rotate it like this. If you rotate it theta degrees, then you'll have a ray B over here. And let's see, quick stuff. So initial side, terminal side, some jargon, which says that the rotation is occurring in this direction. When you're on the unit circle, things going in the counterclockwise direction like this are positive angles. And if you have something going down here like this, that's going to be considered a negative angle right here. This is a negative angle. Okay. So we have positive angle. Oops, sorry, counterclockwise. Counterclockwise is positive. And going with the direction of the clock, we have negative angles like this. So this theta would be negative, and just a convention. Sort of just a take my word for it kind of thing. So you'll probably have heard that a circle has 360 degrees in it. So that means if you start here and you go around the circle, if you take that ray that was pointing here and you rotate that ray to go here and then here, keep rotating it, eventually you get back here and you're at 360 degrees. So that ray started at 0 degrees and rotated all the way around to 360 degrees. Okay. See, another type of unit we use besides degrees is called radians. So what a radian is, I'd like to think about it as what it actually is and understand it, because I remember when I was in Trig, I didn't understand sort of why are we doing this? Why am I converting degrees to radians? It's just an exercise, a thing to do. But now that I understand it, it's sort of funny. I look back at myself and I think, why was that a struggle? Because it's sort of like, how can I unsee it now? The idea is if you have a circle of radius r, so circle is defined by its radius, right? You can have a circle of radius a circle of radius. Oops, that's the diameter. B, circle of radius C. Okay, R is the arbitrary letter we use, meaning some radius. So I don't know what the actual length is. You don't have to get caught up and say, is it 4 centimeters? This could be, 4 centimeters, 50 millimeters. It doesn't matter. A foot. Right now we're just calling it R because there's a fact of the matter about circles and their radii, the radius. If you were to measure out an R length, so again, if this was 4, then you measure out 4 here, right? How many R's, how many radii will fit in this arc right here? Well, it turns out it's pretty convenient. Another thing you may have heard of is that this would be 1r, 2r, 3r, and then a little tiny bit right here, which is about 1.1459, 1.14155. Whoops, 3.14159? Yeah, about that much. And so you'll see, interesting. So the question is, how many R's fit in this arc? And then the arc I'm talking about is this one. How many? The question is answered. We get 3.14159 something something more numbers. Okay, 3.14 is very well known. Constant, pi, very famous. So you'll see now. Okay, cool. So that means that the way to say it in words is if you rotate this ray that I spoke of along here, if you rotate it from here over to be pointing the other direction, well, you've rotated it 180 degrees or pi radians, which is 3.14159 radians. Okay, and I'll put this where it belongs, actually. Okay, so this spot right here is 180 degrees rotated from here all the way around, or halfway around, I should say. And then we can then divvy up the unit circle. So we know this is pi radians, a rotation of pi radians. If the question is, why should I convert radians to degrees and vice versa? The answer is because if you know the degrees of the rotation, then from that you can determine the distance along this path right here. So it's information about the arc, this arc. It's information about the length of that arc that is extrapolated from the information of what angle is it from this chosen, horizontal. Okay? So how do we do that? Just like to draw circles, I guess. How do we actually do it? So we want to do degrees to radians. Well, then we'll say, okay, we have some value degrees over here. And I'm going to say goes to radians. Well, I will make an equation that has a bunch of stuff over here, operations, and then radians by itself, because that's the thing we want to end up with at the end. So we do the angle in degrees times pi over 180 degrees. And so you'll take the number of degrees. Okay, so you have this angle right here. It's usually denoted with this little square if it's a right angle. With this angle, if we know we have a 90-degree angle, right? Then we'll use this equation I just drew and say, well, the radians are going to be equal to the amount of degrees times pi, which is a value in radians. So you're taking a number of degrees and multiplying them by a unit of radians, okay? And then dividing by the number of degrees that this value pi is worth in degrees. That makes sense. Okay, cool. So these degrees cancel. These zeros cancel. So the rad is going to be 9 over 18 is 1 over 2. And there's that pi. This is usually written as pi over 2. Okay, so now we know that an angle of 90 degrees here, that known quantity of 90 degrees tells us that this distance here along this arc is pi over 2. And so this is, remember, just equal to 3.14159 something something, half of that, which is a number that's not super important, but it's close to 1.5, so 1.59. So we proved to ourselves that this part of the unit circle is pi over 2. So the reason that this is pi becomes self-evident eventually, that a 180-degree rotation of this ray over here draws out a 3.14159 unit arc. So then we can start filling this out. So like we just discovered, we showed it to ourselves. That's pi over 2. That's pi. It's 3 pi over 2. And that's 2 pi. The way we got to those is logical, right? You can add 90 degrees from here. Boom, boom, and then you have a half of a pi. If you add another 90 degrees, you're going to add another half of a pi. If you have a half of a pi plus half of a pi, you have a whole pi. So then you keep doing that. The next thing to do, though, is like I said, 45 is a useful thing to know. So this is let's say this is a 45-degree angle right here. I'm going to copy this before I do that so I can keep having circles. Oops. So at a 45-degree angle, we can do our radians calculation. Again, it'll become self-evident when you realize that 45 degrees is half of 90 degrees. So what is half of pi over 2? Well, it's pi over 4. But just using the equation, you have rads equal to 45 degrees times pi on the top. Pi over 180 degrees, 45 over 180. All right, so 45 times 2 is 90. That times 2 is 180. Okay, we get the answer. Pi over 4. So there's a commonsensical reason why 45-degree rotation from the x-axis to the horizontal here yields a distance along this arc of pi over 4, which again is just 3.14159, infinite amount of non-repeating decimals over 4. I learned this trick, which might help you, but again, you're not going to need to use mnemonics or any tricks because you're just going to understand the fundamentals. But here's how I learned it. So they like for you to know 45 degrees, 30 degrees, and 60 degrees. Those are pretty arbitrary. That's how the unit circle is usually taught in high school and college. But there's obviously an infinite number of angles and infinite number of radians along this circle. But that shouldn't be too daunting. It's actually freeing because you realize then, oh, the ones that I'm learning for the test, they're arbitrary. We're just picking these because they're nice. They fit the problems that we wrote, but we chose which problems we want to see. We already know this is pi over 4. This one's pi over 6, pi over 3. Again, if you do this equation, if you do that, then these will pop out, all those. And so pi over 2 here, and you can kind of keep going, right? If you have pi over 4 here, and then you go here, this is technically 2 pi over 4. say pi over 2 is the same as 2 pi over 4. So you have pi over 4, 2 pi over 4. This is going to be 3 pi over 4. This is 4 pi over 4, actually. Right? Because if you have 4 pi over 4, you just have pi. 5 pi over 4. 6, whoops, this is 6 pi over 4 here. 7 pi over 4. And the same goes for this pi over 6. It's a little more janky, but this will be your 1. Here, I'll have to use the highlighter. This will be your 1 pi over 6. This will be your 2 pi over 6. Because again, remember, 2 pi over 6 is equal to pi over 3. And then you have 3 pi over 6. 4 pi over 6. Oops, sorry. Again, 3 pi over 6 is 1/2. 3 over 6 is a half. So 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6. 10, 11, and then we're back to 12. There's your unit circle. And so if you have radians over here, well, like I just explained, it's going to be rad times the unit you want to go to divided by pi, right? And so we can test that if we want to go from radians to degrees. Say we have our 90 degrees again. So we have pi over 2 times 180 all over pi. Well, that's going to be equal to pi times 180 degrees all over 2 pi. So you can do that if you have a fraction up here, as long as it's being multiplied by the other thing on the top of this fraction, then the denominator is actually being shared by this denominator and being multiplied, so you can do that. So boom, then you have 180 degrees over 2, which is equal to 90 degrees. Let's see, complementary angle means that this angle and this angle add up to 90. Okay. Supplementary mean that this angle, let's see, what is acute is less than 90. So any of these are acute. Obtuse is anything here, or sorry, not here, but anything between 90. It's obtuse. Right, this angle, this angle, this angle, those are all obtuse. Okay. And so the next thing is arc length. So you heard me earlier say that if we know this angle, it gives us information about this, the length of this arc, which is called an arc length. Well, I have to caveat now and let you know that on the unit circle, everything we just said about pi over 2, pi over 4, pi, all that, 0, 2 pi. On the unit circle, that's all assuming r is equal to 1, right? So we start by defining the unit circle based on a circle with a radius of 1, which is why it's called a unit circle. Because then when you have a different circumstance where r is not 1, right, then you will be able to take this s is the radius times the angle. So this arc length is s. If r is 1, then this theta needs to be in radians though, but like I said, if r is 1, then say this is pi over 4. Well, if r is 1, then this would be s equals 1 times pi over 4, okay, which equals pi over 4. So it's true of the unit circle, which has a radius of r. But what if the radius is 5 instead? So we have r equals 1, and then this arc right here is equal to pi over 4. But if we stretch it out, I erase these. If we have a bigger circle, see, the radius is going to increase. So that means the entire circle is bigger. Now r equals 5. So this arc length is actually 5 times pi over 4. Does that make sense? So this got bigger. You can see smaller radius, smaller arc length for the same angle. Okay, that's arc length. The area of this piece of pizza right here. So we have a radius r. We have this arc length s, and we have an area of a. Okay, and there's a formula for that. It's going to be a is equal to what? Half the radius squared times that angle. Need to put the angle in there. On the unit circle, since r is 1, say I want to do this. I love this handy dandy 45 degrees. But this is going to be an angle in radians. So if I want to know the area of this, it's going to be 1/2 of 1 squared times pi over 4, which means it's going to be pi over 8. So the area in here is pi over 8. Teachers love to make you solve problems because if you can solve the problem, that means you maybe kind of understand the thing. Okay, so one will say convert. Again, I want to say how many radians do I have? That's going to be equal to the degrees times this unit in radians over this number of degrees, which equates to this pi radians. So you can remember that this whole thing right here is 1. That's why we're allowed to do it. So boom, boom, you have what, 15 over 18, which is 5/6 pi. And then we'll say what, 25 degrees to radians. Radians are equal to 25 degrees times pi. Another thing I've learned is that I want my final answer to be in radians. And so as I start writing the operation to convert the units, I'm thinking, okay, 225 degrees times, you want the thing that's on the top of the fraction in the numerator. You want it to be in the form of units that you're converting to, because it makes sense when you're multiplying times radians. You're multiplying radians times your current unit. That means you're going to get something that now has radians that didn't before. So it's like, okay, radians go on the top because I'm multiplying by radians because I want radians out. And then if I say hypothetically, if I did this right here without the next part, I would have 225 pi, a new unit called degree radians, right? But I'm going to actually divide out what pi is worth in degrees. Okay, so these degree signs are going to cancel. So this is 1.25. So that means this is going to reduce to 1.25 pi, which is in radians. That's what we like, which is 5 over 4. Same thing. Okay. Radians to degrees. 5 pi over 6 to degrees. I'm going to write my value in radians times the unit that I want to go to. That's why it's going to be on the top of 180 degrees. And then this is going to give me radian degrees. So I'm going to divide by the amount of radians that 180 degrees is worth. So, like I said, this 6 goes down here because they're being multiplied, and then the pi's cancel. So you'll have 5 pi over 6 pi times 180 degrees. Pi's are gone. So you have 5 times 180 degrees over 6. Final answer, 150 degrees, which is, just 5/6 of 180 degrees. Makes sense. Then we'll do this one quickly. So I'll show you what the sloppy fast way is. So radians to degrees. And we have 7 pi 4. So that's going to be times 180 degrees over pi. These cancel. 7 times 180 over 4. 315 degrees. Find length of an arc of a circle. That's the symbol for circle with a radius of 10 centimeters made by an angle of 30 degrees. So we know for arc length equals radius times the angle. This has to be in radians for it to make sense. 10. Let's keep our units so we can be good physicists. 10 times. Again, we have to know what 30 degrees is in radians. So like I said, once you get the unit circle down, you'll memorize it as pi over 6. But if we didn't know that, then we could quickly do 30 degrees times this unit of radians divided by 180 degrees. 1/6 of pi. There you go. Pi over 6 radians we're going to put there because that's the angle. And so the final answer is going to be 10 times pi over 6 centimeters. And I think, let's see, that can be reduced right to 5 over 3 pi. And you can multiply that out or just leave it as 5/3 pi. I don't see why that would be a problem. Let's see, circle of, okay, quick sketch. Always recommend a quick sketch because, what have you got to lose? 15 cm. That's the radius. And the arc length of an angle of pi over 3. So like I said, pi over 3 is somewhere over here. So they want to know this S here. And that is radius times angle in radians. This one we don't have to convert. They already gave it to us in radians. It's going to be 5 pi, whatever that number is, centimeters, right? So again, if you want to put it in your calculator, it's going to be 5 times, you can hit the pi button, it's going to do this, right? This many centimeters, which it's like 15 something. There you go. Just in case you want the actual value. The approximate value, actually. They call this is called an exact value. Although it seems less exact than writing this right? But actually, this is just a tip. The fact that we have this ellipsis here, the fact that it goes on, it's inexact. Whereas this, although it appears to have less information, this is known. This is a known quantity, even if the number is 3.141592654 something something. The fact that we know it and we're just containing it in this symbol makes this more exact. So this is the exact value, and then this one, it's technically more sloppy because if you wanted to capture this value in its entirety, you would need to go, right, keep adding these decimal places to show us what is it. Like with a number like this, what is it? Hold on. With this number, this is a big aside, but I don't know. This is what gets me out of bed in the morning. It's technically this. You may have seen it written as this, right? Now we're back to being exact because if you write this, we know that nothing else happens to the threes. It's just threes. It's just threes. Exactly. But when you have 2 or 23, right, then it's 0.08695652217. And there's more stuff. I don't know what those digits are. You have to calculate them. So this is inexact. This is exact. This is exact. Anyway, the aside is over. Area of a sector of a circle. Okay. We remember. I don't know why I have the grid paper because I don't really use it. I'm sorry about that. 60 degrees, 8 centimeters. Boom. We can do this quickly, right? This is R equals 8 cm. This is an angle of 60 degrees. Off the top of my head, I happen to know that that's pi over 3. But again, we can convert it. Pi over 3. Area of a sector is going to be 1/2 r squared times theta. The area of a sector is 1/2 r squared times the angle in radians. So A is 1/2 the radius squared. And again, we're good physicists, so we're going to do units all the way. You can be lazy on units once you're a pro. If you're learning, it's natural to want to leave out the units because they seem like they're tacked on or an afterthought. But when it comes to checking to see if your solution is correct at the end, a major bonus to keeping your units in is at the end of the day, if you get the force of gravity is in meters, if you get a speed that's in like kilograms or feet, right? If you don't get feet per second, you're messed up. You don't have a speed or velocity, I should say. So keeping in your units benefits you, and it's not that hard to do, and it's fun to see them cancel. Look, maybe it's just me. If they don't cancel, they'll come out. Like for example, in this very problem, at the end of this, an area, if you just think about a square, it's going to have square units. So if I had a square with one side that was a 2 centimeter long side, I would expect that at the end, I have a something something square centimeters square. So that applies to all areas. That applies to all two-dimensional measurements that you're doing. So since area is two-dimensional, I'm going to say at the end of this, I can even write it ahead of time. It's going to be something something centimeters squared. Almost certain. I'm 100% certain. Anyway, so let's try. Sorry, 1/2. I didn't even finish writing this. 1/2 this squared. Theta, what's my angle? 60 degrees, pi over 3. It's going to be something something centimeters squared. That's my prediction. Let's see what happens. This is going to be 1/2 times this right here is going to be 64 centimeters squared. And then this is going to be pi over 3. So then we'll have what? I can divide this by 2. That's 32 here. 32 centimeters squared times pi over 3. So it's going to be 32 over 3 pi centimeters squared. Square centimeters, however you want to say it. So we do in the calculator 32 over 2, multiply that by pi. So it's approximately, remember this is less exact, approximately 50.2654 something centimeters squared, which means back in our original circle, that piece that was, what was it here, 60? This piece of the pi, all in here, the area is equal to about 50.3 centimeters squared. Find the area of a sector with radius 12 meters, angle of pi over 4 radians. There's an equation for it, and it's 1/2. Forgot to put this. 1/2 the radius times the angle in radians. 1/2 of 144 meters squared. Pi over 4 over here. That's going to be 1/2 of 144. I should know. It's 6 times 12, 72. 72 meters squared times pi over 4. We can do 72 divided by 4 even, which will give us 18 pi meters squared. And then if you really care, 18 pi is approximately equal to 56.58 something. And that's going to be the area of that spot right here. That's going to be it for that. We have a theta here. We have an arc length here. We have radius here. We have your sector area right there. On my tablet, this shows up as gray, so I've never actually seen it as a color. But I mean, that's quite nice, huh? And then this one is an actual equation. And that's it. Till next time. Maybe I'll write this. A equals 1/2 r squared theta. See you in the next one.